Alright, welcome back to our final video on trigonometric equations, our final video for the nebulous concept that is Chapter 7. This will be the last of what we are going to be doing this semester with regards to traditional trigonometry. Not to say we're done, but this is going to be more or less the last that you're going to see of the Cartesian plane and that sort of thing. So going forward after this, we will take a turn into the wonderful world of polar and parametric systems. More on that later, because right now we have enough on our plate. Right now we have a few more ideas I want us to look at with regards to using trig identities. One more example for that, and then one example of just some good old-fashioned algebra. Because you don't have to break out fancy identities unless you really want to, or more to the point, unless you really need to. You don't always have to do that, and I'll illustrate that here today as well. So let's jump right into it. All right, this is where we were last time. So here's one I want us to look at. And without really worrying too much about all these words here, worry first just about what I'm asking here. I want to find all the solutions to the trig equation cosine 4 theta plus cosine 2 theta plus cosine theta equal to 0. And yeah, spoilers, what I do end up using is the sum to product formula. But let me explain why I did that. Because you don't have to do that, not technically anyway, right? You could try spinning your wheels with double angle for cosine 4 theta, breaking that down into something in terms of cosine or sine squared of 2 theta, and then do the double angle formula again for that, getting cosine to the fourth of theta, cosine squared of theta maybe, and then also here getting sine or cosine squared of theta. And what you could probably end up, if you did this, would be a fourth order polynomial, which would actually double as a quadratic type equation. So maybe you could try doing that here if you really felt the need. You could end up with something cosine to the fourth plus something cosine squared, plus cosine, plus a number all equal to 0. And so you would then have your work cut out for you, because you would have a it wouldn't be a quadratic type anymore now that I think about it. It instead would be a fourth order polynomial type, where instead of your x for your polynomial, you now have cosine theta being raised to varying powers. So you then have to bust out your trig techniques. You would have to use maybe synthetic division or something like that to find the roots of your fourth order polynomial type equation. So let's not say we did. You're welcome to try, though. That door is still open to you. But what I decided to do instead was recognizing, I got cosine of 4 something, cosine 2 something. You know, if I took the difference of 4 theta and 2 theta and divided that difference in half, I would get cosine of theta, right? 4 minus 2 is 2, divided by 2 is 1. So 4 theta minus 2 theta all over 2 is just theta. And wait a minute, there's formulas for taking all these things and getting that exact expression popping up inside of a cosine. And really, once you recognize that, everything else pretty much falls into place, right? Once we have this, once we reduce down, I've got 2 cosine 3 theta times cosine of theta. And that's all being added to cosine of theta. Well, now I can factor. I can factor out the greatest common factor. I can factor out cosine theta. So that gives me that, all equal to 0, which is now true when either factor equals 0, giving me either cosine theta has to be 0, which is true when theta is 90 degrees or 270 degrees, or when this other expression goes to 0, which tells me that cosine 3 theta has to equal negative a half. So doing the arc cosine function, if you really must, cosine of 3 theta equals negative a half at 2 pi over 3. That's what your calculator give you. Alternatively, it would give you 120 degrees. And so it's then your job to recognize, there's actually another place on the unit circle where that's going to work. That's also going to be true at 4 pi over 3, or call it 240 degrees, I think it would be. Call it 240 degrees instead. So your general solution then would be 3 theta, right? Your general solution for your argument of cosine 3 theta is going to be your two values, each plus 2k pi. So then you've got now, after dividing by 3, 2 pi over 9 plus 2k pi over 3, and 4 pi over 9 plus 2k pi over 3. And if you want to go from here to your everything coterminal with statement, you can. This would be everything coterminal with 90 and 270 degrees. And oh boy, 2 pi over 9 I think is 40 degrees? Right, pi over 18 is 10. You quadruple that, you get 40 degrees. So 40 degrees plus 120, or 240. So that's 40 degrees, 160 degrees, and 280 degrees. And this right here is, I believe, 80 degrees plus 120. So that's going to be 80, 200, and 320. I think that's going to be all your degree measures. And hopefully you're starting to agree as well that sometimes writing out the everything coterminal with angle, 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 angle can be a little cumbersome if we get, this far afield of your standard, well, maybe not your standard, but your run-in-the-mill general solution form. Right? As we get too far afield, as we get a little too complicated, we get a few too many solutions, it's getting to be just a little simpler to leave them as this. But that's a style preference. That's my style preference. You have yours. Let's move on. And so what we have now is from before, right? We have now that we can either use trig identities or we cannot, right? We're using as much as we have to use. Picking maybe the right tool for the right job, if you like that idiom, is very true in this case. So let's finally move here to 2 cosine theta equaling 3 sine theta. There's not any identity I have that can turn a cosine into a sine. Not with some extra side effects, not with some extra complications, right? That's not going to be something I can just readily use. Right? I can turn a sine squared theta into a cosine squared theta, but I cannot turn a sine into a cosine, not without things getting really messy. And so, instead, let's just rely on good old-fashioned algebra. Right? We're going to divide both sides by cosine theta. And that's going to get me no cosine, no sines over here on the left-hand side, and just sine over cosine on the right. Well, sine over cosine is just tangent. So ultimately, I've got tangent of theta equals 2/3. That's something that makes sense. That's something we can solve for. Admittedly, you're going to have to use a calculator for it to get the the approximate value of what theta is going to be. And what theta is going to be is the arctangent of 2/3, which is about 0.588 radians, or if you must, about 33.69 degrees. And so your general solutions here is going to be those values plus k pi, or that value plus 180 degrees, which you could represent as either 33.69 degrees or 213.69 degrees. And so in this example, we did not use a single trigonometric identity, except I guess technically for the fact that sine over cosine is equal to tangent. That's all we used here. And so that big long list of identities we've got access to, we didn't have to use a single one. And in fact, if we had tried to use a single one, we would have had quite a bit of trouble. It's a simple fact. We would have had trouble had we tried to do that. You're welcome to try, you're welcome to spin your wheels on that, but I did it, and I don't think it panned out too well. But now, here's a time where we're going to have to use even more. Once again, cosine plus something equals sine, except now that something is not 0. And once again, I don't have any identities that relates cosine to sine, or cosine plus 1 to sine. But what I do have is an identity that relates cosine squared to sine squared. I have my Pythagorean identities. And so now I can channel my inner algebra abilities, right, my algebra techniques. I can square both sides. That's legitimate, although it runs a risk, right? It's still legitimate. And I've got now this expression, right? Cosine squared plus 2 cosine plus 1 equals sine squared. That's what you get from squaring both sides. And sine squared theta is equal to 1 minus cosine squared theta. So after you combine everything and factor out, you've got 2 cosine theta times cosine theta plus 1 equal to 0. Oh, hello, Daniel. I should have suppressed that, sorry. And what we're looking at is three possible solutions, right? Coterminal with 90, 180, or 270. Well, is that really what we have? No. No, it's not. We squared both sides. We took a risk of adding extraneous solutions, right? If you square two negative things, you have two positive things. That's okay, right? Because you still have negative equals negative in the original equation. If you start with positive and positive on each side of the equation, that's okay, because that would square to both be positive. But if you had negative on one and positive on another, that would be an issue, because that would be bad in the original equation, but it would not look bad in the new equation after you square both sides. So we have to check our solutions. And that's going to be checking 90 degrees. Does that work here? Yeah, 1 equals 1. Is it going to work at 180? Yeah. Right, 0, right, negative 1 plus 1 is 0, and sine of 180 is also 0. 0 equals 0. Great. 270, though, not going to work out, because that's going to give me the equation 1 equals negative 1, which is not true. So we have to throw that one out. All my solutions are coterminal with either 90 degrees or 180, which means it's either going to be pi over 2 plus 2k pi or pi plus 2k pi, which you could represent as 2k plus 1 pi, aka all the odd integer multiples of pi. And that's what we got. And that's all we've got. We've now tapped the well dry, right? I've shown everything there is to show in general, right? You can either use identities if you have to, or don't if you can get away with that. Use algebra techniques if you can, or don't if you can't. Use everything at your disposal to find these solutions. That's going to be your job here. And so at this point, we've pretty much exhausted everything there is to say about Euclidean trigonometry. I don't know if that's actually a phrase, but I'm going to use it, right? Your sines of thetas, your cosines of thetas, your functions, your trigonometric functions in the Cartesian plane, that's pretty much done. There's pretty much nothing left that we're going to say in this class about it. We're going to do some more examples in class, obviously, to get you comfortable with what we've done here in these videos, but that's going to be it. Going forward, we are going to move away from the Cartesian plane. We're going to move away from rectangular coordinates, as we're going to start calling it. We're going to introduce new coordinate systems and see what we can do with that. We are going to broaden your horizons, and it's going to be interesting, to say the least, because in those new systems, we are going to be able to do so many things that we could not have done before. And while we're not going to do too much with them, we're not going to run too terribly, frighteningly deep with them in this class, I do want to, at the very least, let you know about the possibilities that lie beyond. And so look forward to that. It's going to be a good time. All right, well, have a good rest of your day, however late or early in the day it is, and I will see you up ahead.